Hi students, as you might have seen from class, today we're talking all about cell transport. Except this time, instead of talking about trucks and tennis balls as their load, what we're really talking about is the cell membrane and how we transport particles in and out of the membrane. Now in class you saw that there are two types of cell transport. There was active and then there was passive. During this video, I'm going to show you guys 5 different examples that fall within those two categories. 3 of them will be passive transport types, and then 2 of them are going to be active transport types. Let's go. You've probably already prepared page 27 entitled it Cell Transport, and like we discussed, we have 2 types. You've got passive, and then we've got active. Remind me one more time, which one required energy? If you said active, you are correct. Active often requires energy in the form of ATP, or just kinetic energy overall. Passive, like a passive person, not going to be doing that much. And this is because of the flow of particles, which direction they're moving. If they're moving from a high concentration to a low concentration, i.e. diffusion, then they're going to be moving naturally and not requiring any energy. This is what we call moving down or with your concentration gradient. Active, on the other hand, is the opposite. It's going to be moving from a low concentration to a high concentration. Highly unnatural movement for particles. Since this is highly unusual, it requires energy to pump them across the membrane, and this is something we're going to call going against your concentration gradient, since you're fighting so hard to force molecules against their natural flow. Now what we're going to get into, like I said, is 3 specific examples for passive, 2 specific ones for active transport, and we'll take another look at the types of molecules used for each. Let's go ahead and actually divide our page down the middle, but this time instead of terms on the left and definitions on the right, we're going to have passive transport on the left and active transport on the right. And I'm going to draw myself like a sample cell membrane. Already kind of going, I'm going to show my phospholipid bilayer as 2 lines in this case. Remind myself that on one side by the heads, those are polar heads, and the inside of the cell membrane is nonpolar. Now, to represent this beautiful phospholipid bilayer semi-permeable plasma membrane fluid mosaic, yada yada yada, I'm going to use this very complex model, a piece of string. So the first thing I'm going to do is just make my cell with a little cell membrane. I've got inside my cell, outside my cell. Let's start to do some particle movement. The first thing I'm going to set up is some oxygen particles. Now oxygen particles are fairly small and they are very neutral. They have no charge. Right now when I'm looking at it, I have a low concentration of oxygen inside the cell and a high concentration outside. Small and neutral particles are simply going to diffuse across the membrane until they reach a nice dynamic equilibrium. At which point, if one particle goes to the outside, another one will come inside, and there will be a beautiful, constantly moving balance, a dynamic equilibrium. And this process of diffusion is going to happen with all small or neutral particles such as oxygen. And that is because small neutral particles like oxygen, high concentration, they can easily pass through the nonpolar section of the cell membrane and into the cell as needed. A special type of diffusion is one that involves water. Water is a small molecule, only having 3 atoms, and we could set it up so that we have a high concentration, maybe outside, a low concentration inside. Water is slightly charged, is something we call polar, but overall it will be able to slowly osmose into the cell, once again until we reach a nice dynamic equilibrium. So osmosis, special name just for water molecules moving from high concentrations to low. So the one that we just saw was water. Special name for it was osmosis. Same idea, high concentration of water molecules, they can osmose or diffuse right across the membrane. They are polar in charge, so this means they'll be a little bit slower, but they should still be able to get across. Now we must discuss a special category of molecules, those with charges. These are things that we called ions. This one in particular, Na+, is a sodium ion. You could also have things like calcium ions, Ca2+, potassium ions, K+. There's a lot of different things that are just single atoms with a charge. Now the interesting thing about these guys is that because they are charged, the membrane is impermeable to them. Try as they might, they cannot cross through the nonpolar phospholipid fatty acid tails. They just can't make it. Chemically, they will be repulsed. So what do you need in order to actually diffuse from a high concentration to a low concentration? That's where our friend, the protein channel, comes in. Protein channels open up a passageway through the cell membrane, allowing charged ions to diffuse until they reach a more dynamic equilibrium. There we go, now we got a more set concentration gradient with an extreme high concentration and extreme low concentration. Like I said, sodium ions cannot get through the nonpolar portion of the membrane, so they're going to use a protein channel to travel on through, a bit like a tunnel or a passageway. And they will continue to diffuse through until they reach their own proper dynamic equilibrium. This is going to be called not just diffusion, but facilitated diffusion. Facilitated because we're having to use our protein channel in order to pass through the membrane. And this is used for charged particles in particular. So the type that we saw, the last type of passive transport, involves small and charged particles. And that's something that was called facilitated diffusion. It's still diffusion because I'm still going to be going from a high concentration of particles to a low concentration of particles. So no energy is required. They will naturally go that way. The only issue is that they need an extra helper. Since normally they're repulsed by the nonpolar portion of the cell membrane, they're going to need a protein channel in order to get across. Sometimes these are also called carrier molecules. Carrier molecules are fascinating. So while a channel is going to offer just a direct passageway for sodium or other charged particles to go through, a carrier molecule looks something a little bit more like a Pac-Man. What will happen is that the charged particles might bind to the inside of the molecule, and that will cause the protein bonds to actually change shape so that they push them through the membrane. My membrane is sticky, and out to the other side. And once it's released it can change its shape back, Pac-Man to the other side, and carry more on over. It also could work in reverse. So now that I have a high concentration on the inside and a low on the outside, it might bind some on the inside, conform, and push them across the membrane, trying to reach that nice equilibrium. Now that we've gone over the three types of passive transport, diffusion, osmosis, and facilitated diffusion, we're going to go to active transport, the one that requires energy. Our first type of active transport usually involves a setup kind of like this, where I have a high concentration of molecules and a low concentration of molecules. You know, a normal concentration gradient. Except in this case, instead of molecules needing to be moved from high to low concentrations, I need to actually move them from low to high against their concentration gradient. And cells do this to maybe get a bunch of potential energy that they can then use to diffuse out later. Now, of course, molecules do not want to be forced against their concentration gradient from low to high concentration. Instead, they're going to have to use an extra little kick, and that kick comes from ATP. ATP is an energy molecule, that when it binds to the protein, gives an extra amount of energy to force the ions across the membrane and against their concentration gradient. You'll need a new ATP molecule every time you force an ion across, because it does require energy to really force them in a direction they don't naturally want to flow. This entire apparatus is called an ion pump. Remember, ion is a small charged particle. Pump refers to the protein itself that works with the use of ATP to force ions against the concentration gradient from low to high. We're looking at our first type of active transport that requires energy and moves against the concentration gradient. This is using ions usually, which are going to be my small charged particles. Except the only difference between this and facilitate diffusion is that I'm moving in the opposite direction. So say I have just a few Na plus ions on one side, low concentration, and a much higher concentration on the other side. And I'm still trying to force it into the cell. I'm trying to force it against its concentration gradient from low to high. We had two molecules that helped us out with this. One was the protein pump. Maybe we'll draw him kind of like this. Just like a bicycle pump, he's going to push molecules from one end to the other with the help of a little friendly molecule called ATP. We're going to learn all about ATP in just a couple weeks. Just think of him as the energy molecule of the cell. And once ATP binds to the protein pump, the pump will actually change his configuration as needed and push our little Na plus ion against his concentration gradient into a more crowded, higher concentration area. This type of transportation is maybe my favorite. You probably have noticed that we've been dealing with small sodium ions, small-ish oxygen molecules, and smallish water molecules, in general small. Let's now talk about large and charged molecules such as glucose. Glucose is an anomaly because since it's so large, it definitely cannot get across the membrane. And even worse, it can't fit through a protein pump. It's just too large. However, we know that we need glucose to be able to get in and out of our cell somehow. The cell needs glucose for energy, and he's going to export glucose for other cells to use. So, how do we do it? We do it using another little bit of membrane, except this time it will be wrapped up in a sphere, and it's called a vesicle. This small bit of membrane will wrap itself around your large particle, and then it can transport it throughout the cell by going along those microtubules you all learned about last week. Now, what the vesicle does, say we're trying to get the glucose out of the cell, is he will actually go up to the cell membrane, and because he's part of membrane, he will simply fuse with the cell membrane and push the glucose molecule out. This process is called exocytosis. Exo because it is exiting the cell, moving out of the cell. Cyto generally means cell itself. So as you can see, we're adding on to the cell membrane, and it involves the entire cell moving to actually transport this molecule. And finally, remember, exocytosis is used for things such as large molecules, like glucose, ones that cannot easily pass through a protein channel or carrier or pump, and neither can diffuse easily across the membrane. Now, this process can also work in reverse. Say I have glucose outside the cell that I want to bring in. The glucose will be nicely packaged for me in a membrane-bound vesicle. My vesicle will then approach the cell membrane, fuse with the cell membrane, combining with it, and dumping glucose into the cell, expanding the cell membrane. This process is called endocytosis because it moves into the cell. It is entering the cell. And once again, it's for large molecules only. Just realized we forgot to write our first type of cell active transport. That is an ion pump. Now let's talk about the ones we were just showing you guys, which was our large molecules, such as glucose. Say that we have Let's put him here. Our large glucose molecule, nice little hexagon shape. Our glucose molecule, in order to be transported, is going to be surrounded by a vesicle, which is just a sphere shape of membrane. Also made of phospholipids. I sometimes call these my vesicle vans because they're going to drive right on up to the membrane. They're going to fuse with the membrane, and they're going to allow glucose to be expelled. Sometimes I can kind of show this maybe a little bit this way. And in this case, I would call this exocytosis. Exocytosis, remember, is exiting or going out of the cell. Now, if this was happening in the opposite direction, where I was actually going into the cell, fusing and releasing my glucose on the other side, I would call this endocytosis. Endo sounds a lot like enter. This is going to be going into the cell. That's cytosis. So there you have it. We have 3 types of passive transport: diffusion, osmosis, and facilitated diffusion. We've got 2 types of active transport: ion pumps and then exocytosis or endocytosis. Passive happens naturally. Molecules are diffusing down their concentration gradient. Just depending on the type of molecule, they might require a protein channel or not. Active does not happen naturally. It requires things like ATP or energy molecules to force molecules against their concentration gradient from low to high. Or it involves quite a bit of work with the cell membrane, in which a small vesicle will actually come up and fuse with the cell membrane to release a large molecule, or vice versa. A vesicle will come to the cell membrane, fuse with it, and release a large molecule into the cell. So fortunately, that is all for today. You do not have homework other than finishing up this Ed puzzle. Remember, you need to check into Microsoft Teams at 7:40 a.m. tomorrow morning to be counted as present for the day tomorrow. And we will go over many more practice questions regarding cell transport then. See you then. Also, check those eggs.